In this video, we're going to discuss basically how to compute the pullback. So the first thing is how to compute the pullback of one-forms. So recall that if f is a function from Rn to Rm, so coordinates here are x1 through xn, f1 through fm, then if I want to compute f pullback of dfi, this is exactly the ith row of df. And we figured this out using polar coordinates. So I'll just go back to that example. So remember that f pullback dx, not dd, dx, is cosine theta dr minus r sine theta d theta, and df is the matrix cosine theta sine theta negative r sine theta r cosine theta. So you can see that, the first row and f pullback dx are the same. And what this means is that in general, f pullback from one-forms on Rm to one-forms on Rn is precisely df transpose. So you have to be a little careful about this. Df basically gives you f push forward, df transpose gives you the pullback. And it can be a little bit confusing, but doing a lot of computations helps. So what you can see here is exactly when I take the transpose of this matrix, cosine theta, negative r sine theta, r cosine theta, and apply it to the vector 1, 0, which now as a one form on R2 represents dx. This is exactly the vector cosine theta, negative r sine theta, which will represent cosine theta times dr minus r sine theta times d theta. So the next thing we want to do is prove three properties. So the first one that will help us compute the wedge product, or sorry, the pullback. So the first one is just that the pullback is linear. So I actually will not do this one in the video. You can look at the proof in the book, but it's really straightforward, or you can prove it on your own. The second one is that the pullback basically distributes over wedge products. So if I want to compute the pullback of a wedge product, I just compute the pullback of each term and then take the wedge product. So this is pretty easy to prove using the formula for the wedge product. So f pullback alpha wedge beta applied to v1 through vk plus l if beta is a k form and beta is an l form and alpha is a k form. This is just alpha wedge beta f push forward v1 through f push forward vk plus l. And this is this, use this formula, sum over sigma and sk plus l, sine of sigma, alpha of f push forward v sigma of 1, f push forward v sigma of k times beta f push forward v sigma k plus 1, f push forward v sigma k plus l. And then this is when I actually go back and unravel this as I can rewrite this as 1 over k factorial L factorial, sum over sigma and sk plus L, sine of sigma, and then this is going to be the pullback of alpha applied to v sigma 1 through v sigma k times the pullback of beta of v sigma k plus 1 through v sigma v sigma k plus L. And then this is just exactly by the definition of the wedge product, f pullback alpha wedge f pullback beta applied to v1 through vk plus L. So the third and final property is that f commutes with d. So f pullback of d alpha is d of f pullback alpha. So this proof is in two parts. So the first part is we're going to prove when alpha is a zero form, i.e. it's a function. So this actually requires us to define what f pullback alpha actually even means in this situation. We're going to define f pullback alpha to just be alpha composed with f in this situation. And then in this case, what we need to show is that we need to show this identity. So f pullback alpha, f pullback d alpha applied to a vector v is d alpha f push forward v, which is d alpha df applied to v. So this is big D. And then because alpha is a zero form, so it's a function from Rn to R, little d and big D are the same thing. And then this is just using the chain rule, d alpha composed with df of v, which is d of alpha composed with f of v, which is exactly what I wanted, because now alpha composed with f is also a function from Rn to R. So this is d of f pullback alpha applied to v. So now we need to prove the identity in general, and this sort of video illustrates the utility of the two different definitions of the wedge product. So I want to prove that f pullback d of some general k form is d of f pullback of the k form. So let's first compute d of this, f pullback sum over I, dai wedge dxi. And now let's compute f pullback. So because of the first property, pullback being linear, I can put the f pullback inside the sum. And because of the second property, I can compute f pullback of each term in the wedge product separately. And then because property 3 is true for alpha a being a zero form, so a being a function, this is df pullback ai wedge f pullback dxi. So this I need to now break it out into f pullback dxi1 wedge all the way out to dxi k is a k form. Sum over I d. So this is d of f pullback ai. Now wedge. I guess I don't need this second parentheses. Wedge. So because f distributes over the wedge product, and because it commutes with d for zero forms, I get d of f pullback xi1 wedge all the way out to d of f pullback xik. And then this is exactly the sum. So this is exactly applying d to, right? So this is just like f pullback of d. I mean, I can also write this as f pullback of dxi. Whereas, and this is f pullback of ai. So the fact that, so basically this part all together, so this is d sum over I. This is d of f pullback ai times d times f pullback dxi. And then I can pull the d out because d is linear. Okay, so that proves all the properties, which will help you compute pullbacks.